Welcome to the next lecture in quantum chemistry. In the previous class, we were trying to understand how a rigid rotor problem can be solved for a quantum mechanical system. So we were talking about two bodies, M1 and M2, that are separated by a distance r, that is the bond length, and we were able to realize how the Hamiltonian that was written as in the form of a Laplacian gets converted into the spherical polar coordinates. And how did it look in spherical polar coordinates? The Hamiltonian ended up becoming minus h cross square by 2mr square 1 over sine theta d over d theta sine theta d theta plus 1 over sine square theta dou square by dou phi square. This is how the Hamiltonian was written. This is for the system where r is constant. After having done this, we set it to motion with the h psi equal to E psi equation. Having done that, what we were able to achieve is break this entire equation into a part that contains only theta plus a part that contains only phi. Then we equated it to 0. And we were able to realize the phi part was indeed the solutions for particle in a ring, and therefore what we were able to find, the capital phi portion, comes up as 1 over square root of 2 pi exp I m phi, where m can take the value 0, plus minus 1, plus minus 2, and so on, where the ground state m equal to 0 is singly degenerate, while that of plus minus 1 and higher ones are doubly degenerate. And the energy for such a system was given by m square h cross square by 2I, where I is the moment of inertia. Having solved this, we left the lecture at a point where we said the quantization of L also comes through. Let's rewrite that portion of the equation so that we recollect where we left off. Sin theta divided by capital theta dou over dou theta sin theta dou capital theta over dou theta plus beta square sin square small theta times capital theta is equal to m square. This is where we left off. I think it was beta that we assumed. Then we learned that if beta, when solved by the power series, is L into L plus 1, where the beta was initially set as 2IE by h cross, this would imply EL will come up to be h cross square by 2I L into L plus 1. So this is essentially where we left the previous class for the rigid rotor problem. In this class, we will continue to understand, now having understood the energies of this L quantum number, we'll be trying to understand how the wave function looks. And in this case, we will have to go through a series of steps. We will still not solve the entire problem. What we will end up doing is that if x is set as cos theta, remember the range of theta is between 0 and pi. This indicates the range of x will be between minus 1 to plus 1. Having done this, what is dx going to be? It's going to be minus sine theta d theta. So this implies d theta equal to minus dx by sine theta. Therefore, what is going to end up happening now is that we need to convert this equation in terms of x. So let's start doing it now. So let's keep it at sine theta right now, divided by capital theta, dou by dou theta, sine theta, dou capital theta by dou x, divided by sine theta, because that ends up coming here. Of course, sine theta is 1 minus x square the whole square root. Let's not write it right now. We will simplify it and then write it later. Plus L into L plus 1 sine square theta times capital theta is equal to m square. Having done this, we are able to realize that it's sine theta divided by capital theta sine square minus sine square of theta dou theta by dou x plus L into L plus 1 sine square theta times capital theta is equal to m square. So now what we are able to realize is that this now becomes minus x square, 1 minus x square. And then if you set the capital theta to Legendre polynomial in Px, Legendre polynomial, this equation ends up becoming 1 minus x square divided by capital theta, because there will be a sine theta that ends up coming, dou by dou x. Minus of a minus would become plus, so you have something like 1 minus x square dou p over dou x plus L into L plus 1 sine square theta times p equal to m square. Of course, there's a p right here. Is this right? Now it appears that there will be no theta here. Yeah, there will be no capital theta here. It's a small mistake that I have done. So there will be, the denominator will be p. So having done this, the next step is to differentiate. As you have u times v, this is going to be 1 minus x square by p minus 2x dou p by dou x plus 1 minus x square dou square p by dou x square plus L into L plus 1 minus x square equal to m square. So this would finally end up being, if you are able to see, there's a 1 minus x square everywhere. So if I cancel it here, you're going to get it in the denominator here. Having done this, let's quickly rearrange. Let's also multiply the entire equation by p. This will end up becoming 1 minus x square dou square p by dou x square minus 2x dou p over dou x plus L into L plus 1 minus m square by 1 minus x square times p equal to 0. So this is how the equation finally reduces itself to. So let me rewrite this equation so that we can start discussion from there. 1 minus x square second differential of p with respect to x minus 2x dp over dx plus L into L plus 1 minus m square by 1 minus x square p equal to 0. So this is the equation that we have finally ended up with, and this equation is what we will end up solving, and this is solved using the power series method, which once again we had discussed in the harmonic oscillator problem. This works out in a way such that p comes up as the Legendre polynomials for values m equal to 0, such that I'm going to show you a few Legendre polynomials where P of 0x is equal to 1. So we generally tend to write P of L times x equal to a function of x. So P of 0 indicates that for the value L equal to 0, and P of 1 of x is nothing but x itself. Here L value is 1. P2 of x is 1 over 2, 3x square minus 1. Similarly, P3 of x is 1 over 2, 5x cube minus 3x, and so on. Okay, so now that we have solved, or at least we see the solution of the rigid rotor problem in terms of the Legendre polynomial. One way of seeing whether this is indeed true is to just apply back these functions in this equation, where you will be able to see if you apply x, and you will be able to satisfy the this given differential equation for m is equal to 0. One important aspect that we are able to realize is that the functions alternate as even and as odd functions. Okay, so when L is even, the functions are also even. When L is odd, the functions are also odd. Right? So having seen this, this is an important conclusion for one to make. The way generally the normalization, or rather, generally once you have a solution for a given Hermitian operator, you know that the functions of these are in fact orthogonal to each other. So meaning that when you integrate over the entire space of x with respect to PL of x times PL prime of x, this will be equal to 0 when L not equal to L prime, and this will be equal to 1 in the case that they are normalized. So how would we end up normalizing this? We would once again normalize this between minus 1 and plus 1, such that dx of PL of x the whole square is set to 1, and a little bit of algebra tells you you're going to end up getting something in relation with respect to the L value. Of course, having understood this, we know from the initial equation that m square and L are related, meaning for values of L, m is also going to associate itself with a certain set of values, meaning that m is not always equal to 0. In all the cases, m also has non-zero values. So this can be deduced from the Legendre polynomials, as these are called associated Legendre polynomials. So how do we get them? We would be able to get them. PL of mod m as a function of x is going to be given by 1 minus x squared with a mod m over 2 times d power m dx power m PL of 0 for that value of x. So meaning that the moment you get to know what are all the Legendre polynomials associated with m equal to 0, you will be able to deduce any of the other ones. So why don't we take a quick look at one of them. So let's take a look at what is P00 of x. We know for a fact x square 0 by 2 d0 dx 0 of 1. So this is going to be ending up as 1. This is all you are going to have. On the other hand, when we go for P1 of 0, which we know for a fact, which we just learnt a moment back, is nothing but x itself, right? So P1 of 1 of x is going to be given by 1 minus x square mod of 1 over 2. The reason why we get a mod, because L and m square are related to each other in the initial function that we ended up deriving. So therefore, it's going to be invariant to plus minus 1. Okay, so having done this, d by dx of the first function, which is going to be x. So this will end up being square root of 1 minus x square. So let's do it for P2 of 1 of x is going to be 1 minus x square 1 by 2 d1 the first differential with respect to the second Legendre polynomial, which is 1 over 2 3x square minus 1. So what will this end up be? Differentiation of 3x square will be 6x. There is a 2 here. Therefore, you will end up with a 3x. So this is going to be 3x times square root of 1 minus x square. So let's do it for one more function. Let's do it for one more associated Legendre polynomial. Let's also do it for P2 of 2. Remember, for values L equal to 2, m takes value of 0, m takes value of plus minus 1, m takes value of plus minus 2. Okay, so therefore P2 of 2 is going to be 1 minus x square 2 by 2 d square by dx square 1 over 2 3x square minus 1. So what the first differential will be 3x, the second differential will be just merely 3. So this is nothing but 1 minus x square. So let's rewrite whatever we learned so far. So P0 of 0 is going to be 1. P1 of 0 is going to be x. P1 of 1 is going to be square root of 1 minus x square. P2 of 0 is 1 over 2 3x square minus 1. P2 of 1 is 3x, the square root of 1 minus x square. P2 of 2 is 3 1 minus x square. And we know that x was given by cos theta. So we should be able to convert this back. So this is going to be equal to cos theta. This is going to be equal to square root of 1 minus cos square theta. That is going to be sin theta. And this is going to be equal to 1 over 2 3 cos square theta minus 1. This is 3 cos theta sin theta. This is going to be equal to 3 sin square theta. So let me draw lines. So what ends up happening here, you are able to realize when L is equal to 0, this goes as x power 0. When L equal to 1, it goes as x power 1, which is in terms of cos theta and sin theta. When L equal to 2, you have x power 2 that's dependent on it. So therefore, you're going to get 3 cos square theta minus 1, 3 cos theta sin theta, and 3 sin square theta. Good. The main reason why we ended up converting it back is that Legendre polynomials, we end up writing for the rigid rotor in terms of the respective cos theta. Because x doesn't make sense, we always write in terms of theta here because that's what we started with. The only reason we converted it to x was the mere fact that we are able to solve it using the power series in the x dimension. So similarly, let's try to look at how the orthogonality will look. So whatever we had, dx of PL of x, PL prime of x dx, which is what we had before, which we said is 0 when you had L not equal to L prime. We need to convert it back to theta. So this is going to end up being 0 to pi sin theta d theta. This is important because this is the integrand that ends up coming. One might wonder where is the minus sign gone when you have a dx differentiation that has gone into inverting the integrals. So once you have something like this, you have PL of cos theta, PL prime of cos theta, that is equal to 2 over 2L plus 1 dou L L prime. So this is nothing but our Kronecker delta that we have seen several times, and this is nothing but the factor that would come when you want to normalize. So you're able to realize when m equal to 0, this will become the normalization functions. So how would we do the normalization, or how does this relation look for the associated Legendre polynomials? So this is going to end up looking something of this sort. Integral 0 to pi sin theta d theta, it's the integrand that ends up coming. That is going to be equal to P mod L of cos theta, PL prime mod M cos theta, will be equal to 2 over 2L plus 1, which we are just merely borrowing from there, L plus mod m, the whole factorial, divided by L minus mod m, the whole factorial, of course with dou L L prime. Right? So now what this ends up doing is that one could easily normalize this function, where the normalization constant NLM that comes from this portion will be equal to just the inverse of it, 2L plus 1 divided by 2 times L plus mod m, the whole L minus mod m, the whole factorial, and L plus mod m, the whole factorial, with a square root. The square root comes because of the fact that you are going to have a psi star psi that is going to be equal to 1. Psi star psi d tau integrated over the entire region is going to be equal to that. So now we are finally ending up with the solution of what are the spherical harmonics. So you're going to have phi comma theta comma phi, which is going to be given by capital theta times capital phi, and we knew that the capital phi was given by 1 over square root of 2 pi e power I m phi, right? Having done this, we need to just multiply this with the Legendre polynomials. So this is going to end up behaving or looking like this: 2L plus 1 divided by 2 times square root of 2 pi. All these are within under root, so it's going to be 4 pi L minus mod m factorial divided by L plus mod m factorial, the whole under root 1 over 2 PL mod m of cos theta, this is the theta part, times e power I m phi. And the most important things are L goes between 0, 1, 2, 3 and so on, and m goes 0, plus minus 1, plus minus 2, plus minus 3. And the condition here is that m will be dictated by L. For instance, if L is 0, m can only take the value 0, and when L is 1, m can take the values plus minus 1 and 0. Basically, it's going to increase the number of levels. So what is that going to end up doing? So let's do it for a few set of cases. L equal to 0, m equal to 0, L equal to 1, m equal to 0, plus minus 1, L equal to 2, m equal to 0, plus minus 1, plus minus 2, L equal to 3, m equal to 0, plus minus 1, plus minus 2, plus minus 3 and so on. And we are able to understand here that 0, 0 is single value, this is 3, this is 5 and this is 7. Therefore, the level of degeneracy with respect to L will go as 2L plus 1. This is very important for us to remember and understand, as it will come back in other cases. Of course, the orthonormality that will go in this case for the entire function will be 0 to 2 pi of d phi. D phi doesn't have an integrand except for d phi itself, and 0 to 2 pi sine theta d theta with a y L m theta comma phi star, which is a complex conjugate, y L prime m prime theta comma phi, which will be given by Kronecker delta that relates L to L prime, Kronecker delta that relates m to m prime. So this is the overall function that ends up coming for the harmonic oscillator. So where did we start? We said the Hamiltonian will help us determine what are the functions. So this is our function. The eigenvalue equation is rewritten here, L into L plus 1 divided by 2i. This indicates that if you operate Hamiltonian on the spherical solutions of the spherical harmonic, you get a constant back and the function back up. So this is the eigenvalue equation, that is the Schrodinger's equation that we started with. And as you might remember, the Hamiltonian is given by L square by 2i. So this once again makes you understand why Lm is an eigenfunction of both Hamiltonian and the angular momentum operator. So quickly rewriting all this, when you normalize each of these functions, what ends up happening is that you would be able to write each of the spherical harmonics. We will quickly write that and finish up this lecture where you're going to have y0 of 0, that is going to be given by 1 over square root of 4 pi. Then you have y1 of 0, that's going to be square root of 3 by 4 pi, which is the normalization constant that goes with cos theta. And y1 of plus minus 1 is going to be given by square root of 3 by 8 pi sine theta e power plus minus I phi. So how does the sine theta come up? We had done that a moment earlier. The sine theta comes up from the fact that we were able to get it from the Legendre polynomial, and the e power I phi comes from the m portion. So let me repeat it again. This comes from the m portion, this comes from the L portion, this is the overall normalization constant. So let's write the same solutions for y 0, that is going to be equal to square root of 5 by 16 pi, 3 cos square theta minus 1, y2 plus minus 1 is going to be given by square root of 15 by 8 pi times sine theta cos theta e power plus minus I phi. Y22 is going to be given by square root of 15 by 32 pi sine square theta e power plus minus 2I phi. Okay, so these are nothing but the solution of the spherical harmonics, which we will soon see will turn out to be the orbitals of the hydrogen atom when we end up solving it. I hope this lecture was helpful enough for you to understand how the functions of the rigid rotor are solved. Although we don't solve it, we are able to see how the functions will end up looking, and hopefully we will be able to simulate them as we go forward, how the solutions are helpful for us to understand chemistry and its applications. Thank you.